Hello, everyone. It's my great pleasure to present autonomous navigation technology for smart cities. I'm Professor Myung from KAIST. So this shows the animation of our developed system, like the autonomous surface vehicle and wall climbing drone. Let me explain these features in more detail in my presentation later. Okay, our lab is named as Urban Robotics Lab. So we develop the robotics technologies for smart cities. We are focusing on the development of robot navigation technologies such as vision-based or LiDAR-based or magnetic-based 3D SLAM. And also we make some technologies related with the self-driving car. And also we are concerned on the unmanned aerial vehicle. Autonomous navigation of this vehicle is very important in the inspection. And we are also making some unique robot called Morbot. This is for the underground digging. So we use the underground localization technologies for this Morbot. And also we developed the deep learning-based semantic navigation technologies. And using these fundamental technologies, we have some applications like structures monitoring and environmental robotics. In the structures monitoring, we developed the 6-degree freedom strict health monitoring robot system, and also using the wall climbing drone, we inspect the buildings to other bridges. And also we apply these technologies for fire disaster situations. So scouting robot has been developed. So let me also briefly introduce this Pharos. And the last one is the environmental robotics. So we use our navigation technologies for this environmental surveillance and rehabilitation. So Zeros, jellyfish elimination robotic swarm has been developed in our lab, and oil spill percussion robot and green edge removal robot have been developed in our lab. In our lab, we developed some AI and robot intelligence technologies. So for the autonomous robot navigation, we use the vision, LiDAR, and magnetic field for the SLAM, simultaneous localization and mapping. We use these SLAM technologies for various environments like indoor, outdoor, including the ground, underwater, underground, aerial situation. And object recognition is very important also for this autonomous robot navigation. So UAV, image-based some object recognition, and object recognition using low resolution aerial images has been investigated in our lab. And human behavior recognition for HLI is also very important for this robot navigation. So human pose estimation and sequence-based human behavior recognition has been developed in our lab for intention recognition of the human. So there are some developed robot systems in our lab: Zeros, Eros, oil spill protection robot, and Keros, Pharos, and Morbot. So let me briefly introduce about these robots developed in our lab in the later slide. Okay, the first one is the autonomous robot navigation technology is developed in our lab. There are core technologies for autonomous navigation. As you already know, the mapping and localization is very important, and doing these two things at the same time is called the SLAM, simultaneous localization and mapping. There are two major SLAM approaches actually, Bayesian-based and graph-based. Bayesian-based approaches usually concentrate on the current level pose, and they usually use the filtering techniques like the comma filter or faster SLAM, particle filter, and so on. They augment the robot state with the landmark state, landmark or the feature state. So they solve these localization and mapping problems at the same time by augmenting these states at the same single state. In the graph-based method, we are concerned about the robot's full trajectory from the start to the current pose. So we form the graph structure using the nodes and constraints concept. So if we have some odometry, then we connect them with the constraints. And if we observe some features, then we also make the constraint. By forming those constraints between the nodes, we perform the nonlinear optimization using the least square, nonlinear least square method, like SAM, iSAM, GT-SAM, G2O, and so on. The solution of the SLAM problem can be computed with the configuration with the minimal energy like this. So if the robot proceeds like this way, they form the constraint, and this is somewhat like the springs connected with each other. So if they have very strong constraint, then that can be connected with very strong spring. And if they are connected with very weak constraints, then they are considered as the weak spring. So overall, we make these nodes and constraints and minimize the overall energy by reducing this difference between the prediction and the measurement. So this is called the residual, and the residual should be optimized over all the robot state. So if we have the minimization, then we can get the robot's full trajectory. In our lab, we are developing the graph-based sensor fusion technology for dynamic and feature-full environment. So we remove the force constraints in dynamic environment, such as the low and high dynamic environments. And the SLAM performance can be improved using the low-cost sensor fusion. For example, 2D LiDAR combined with a 2D camera. We do the 3D matching for robotness. And magnetic features are combined with the 2D LiDAR, and we can minimize the planar localization error. So if you think about this environment, then there can be some feature for environment like the corridor. There we have the LiDAR feature for environment. In the space like this rectangular space, then there are some magnetic feature for condition. So by combining those sensors and fusing them, we can make the robust localization result. So we fuse the LiDAR, magnetic camera sensors information and form the graph and perform the optimization. This shows the graph-based 3D SLAM technologies developed in our lab. We use the RGB-D data inputted, and using the fast image extraction algorithm, DH-SURF, we have developed this one and forming the graph and optimize this graph. And in doing the optimization, we perform this GP-SLAM. So this is the abbreviation of the grouping nodes and pruning constraint SLAM. So this actually deals with the low dynamic environment. So by performing this SLAM, we can recover the lowest full trajectory as well as obtaining the point cloud map of the environment. Okay, this shows the indoor experiment. So using the RGB-D sensor, we match the frame by frame. And as you can see, we perform the 3D SLAM technologies and make the 3D map, 3D point cloud map of the environment like this. So if we have the loop closing, then it will be optimized like this. So we now can get the sharp and clear 3D map of the environment like this way. So we perform the GP-SLAM for low dynamic environment. Low dynamic refers to the environment where the dynamic object moves very slowly. So for example, if the robot traverses like this way, in doing that, the object in here has been moved like this way. So if the robot gets to the same point, then you cannot get the same object at the same place. So if you perform the 3D slam naively, then this will deteriorate the trajectory. So to prevent such kind of situation, we developed this GP slam. So first step for GP slam is the grouping nose. So we measure the normalized covariance like this way. And if the covariance value is less than some threshold, then these can be grouped as the same group. So the nodes belonging to this group is grouped as G1, and the second one is grouped as G2, G3, G4, G5, and so on. And then the second step is pruning force constraints. If the robot faces this kind of situation, actually G2 and G6 should be the same, but now because the object in here has been moved to the other place, G2 and G6 have some kind of error. So if we have the error metric based on the grouped nodes, then we can make this kind of graph. So this is the node group 2, and this is node group 6, and they have big difference. So edges between groups 2 and 6 can be pruned by using this table. So after that, we can make the clear and optimized paths like this. So we do this two-step grouping nodes and pruning constraints for this GP slam. So this video shows the GP slam for dynamic environment. So this is the result from the visual odometry, and this is the result from conventional graph-based slam, and this is the result from GP slam. So you can see the difference between them. So we have the clear 3D map, as you can see. That means we have the good localization accuracy. So this video will show that. So we extract the soft features from the environment, and you can see that there are some constraints. And if the user moves this object to the different place, then the conventional graph slam, denoted by this red, yellow line, will be deteriorated. But the proposed method will generate the exact 3D map of the environment. Okay. We use the 3D slam techniques for autonomous driving also. So we first make the 3D point cloud map of the environment, and by matching this 3D point cloud map with a stereo camera, we can localize the vehicle. So this shows the result. So this is the pre-built 3D point cloud, and this shows the 3D map image and the current image matching. By matching these two, we can localize the vehicle in spite we have the GPS denied environment. So this has some roof, so we have the GPS denied environment like this, but using the odometry and the vision, we can make the correct trajectory of the robot. Okay. We also deployed our algorithm for Singapore area. So this is the vehicle, and we use the 3D LiDAR sensor, Velodyne, for this 2.8 kilometers trajectory. So as you can see, we have the good localization accuracy, and the mean error is less than or equal to 0.1 meters. So this is quite accurate result. As you can see, the IEEE RLA paper we have published in 2017. Recently, we have developed the 3D slam techniques using a tilted 2D LiDAR sensor. So we just used the 2D LiDAR, but it is somewhat tilted like this. And if you move around, then the robot will generate this kind of local 3D point cloud map. And this local 3D point cloud map will be stitched together to form the global map. And in stitching these maps, we use the hierarchical graph optimization techniques developed in our lab. So before the global optimization, we have some discrepancy between those nodes, but if you perform the second stage of the global local optimization, then we can see that they are in good agreement. So using this tilted to the LiDAR, and this is for the comparison. So ground truth has been taken from this RTK GPS and also from this yellow-line LiDAR. So we have tested in the outdoor parking lot and also indoor and outdoor environment. So by applying our technique, we can build this 3D map of the environment by using just this 2D LiDAR. This video will show the optimization result. So this is very quick, and using this 3D map, we can make the robot navigate around this area. So this is the robot equipped with this 2D tilted LiDAR. And if we make some waypoint, then it will navigate through this indoor and outdoor environment automatically. So in spite of the disturbance from the human, this robot will recognize the location accurately and navigate through this outdoor and indoor environment. Okay. And we have also developed the GP-ICP called ground plane ICP. And in the conventional ICP, they are usually based on the Euclidean distance between the feature points. And this can yield wrong LiDAR matching. So we limit the search for matching within similar heights for ground vehicles. So if you just apply the conventional ICP like GICP, generalized ICP, then we have some mismatchings like this. Trees are mismatched with the ground, as you can see. But if you apply this limitation, constraints, then we can obtain the precise matchings between the scans. And also, we can accelerate the computation by layer computation of these matchings. So in this video, you can see the comparison between generalized ICP and our proposed method. So we have successfully found the matchings, but GICP failed in this situation. So if you plot the success rate, then our method outperforms the other methods, as you can see. You can refer to the details in this paper in IEEE Access. So we have also applied our hierarchical graph SLAM using the tilted Velodyne 3D LiDAR. So using this 3D LiDAR and by applying the previous hierarchical graph SLAM algorithm, then we could optimize the campus map and also the Seoul area map. You can see it is optimized like this, and also you can see the graph is optimized after several iterations. So this green indicates the odometric result, and the red line indicates the optimized result. So we used our techniques for self-driving car. So in the KAIST environment, we have built this 3D point cloud map and matched this one with the current scans from the LiDARs. Okay, we have the GPS and IMU installed, and 64-channel LiDAR, and also two 16-channel LiDAR. Okay, so we also use the high definition map information, and by matching this high definition map with the current observation, we can localize the vehicle also. We first generate the green line using the path planner, and then this vehicle will follow this path like this way. So what happens, we have the feature for environment. The vision and LiDAR sensors are usually in the feature for environment. So in that situation, we have developed this Earth magnetic field based slab. So we actually use the anomaly of the Earth magnetic field like this. This is the 3-axis magnetic field distribution. As you can see, we have the great distortion in the magnetic field in the indoor situation. So we use this property, and also the matching of the magnetic sequences are used. So if the robot proceeds like this way, then the magnetic sequence is generated, and this sequence will be matched, and we have the loop closing in the slab. So this is the result for the building environment. So if you traverse the corridor like this way, then if we have the same place, then we have the loop closing here and loop closing again. So we correct the position of the robot like this way. So this result is quite comparable to that of the result from the LiDAR. So cyan indicates the SIG LiDAR mapping result, and the blue one indicates the optimized pose graph. So you can see that they are in good agreement. And the advantage of this method is that we can also make the magnetic map of the environment. So if the user enters this area and matches his magnetic field footprint with the previous magnetic field map, then we can also localize the user in this environment. So sensor fusion between the magnetic field and RGB-D sensor has been performed in this environment. You can see that this portion indicates the vision matching, and this portion indicates the magnetic field matching. So this is the generated magnetic field map. And using the Gaussian process, we also estimate the magnetic field map nearby the robot's trajectory. And if they are matched, then you can see that feature matched. This means the vision features has been matched, and it is plotted in here. The covariance has been matched in here. And if we have some magnetic matching, then it indicates the magnetic bundle matcher. So magnetic bundle matcher occurred here. So we have the covariance in here. So by combining these two sensor information, we can make the correct pose of the robot. Okay. And also we apply this one to the underground localization. We actually use the two IMUs installed in the front and the rear. And by matching these two magnetic sequences, we can localize the vehicle in the underground. So this is the magnetic footprint from the front one, and the second one will be matched. And if we have the backward movement, then we have the very similar magnetic footprint. So using this reflected magnetic footprint, we can match the signals, and using this concurrent normalized cross correlation, we can make the matching. So we have developed this embedded directional drilling robot called Morbot. So by mimicking the digging behavior of the moors, we have designed our Morbot. So this is the Chisel-tooth digger. This is the humeral rotation digger. So this digger actually uses the scoffler. So we mimic this scoffler and also mimic this crushing property of the teeth. So we have designed this expandable drill bit and four-limb mechanism. This is the 3D rendering of the robot, and this is the prototype of the robot. And this is the expanding and folding motion of the drill bit. This property is from the Chisel-tooth digger. To remove the soles, excavated soles, we designed this four rims mechanism. So this is from the second type of digger using the scoffler. So we can make some direction by using the waist mechanism, and also moving forward and locking to the hole using this locomotion mechanism, using the caterpillar. We can localize the Morbot. So this is the scheme. We use the two magnetic data, and if they are matched, then we form the constraint and perform the graph-based slab. So this actually measures the robot's position in real time. So X, Y coordinates are plotted in here in real time. Okay, this is the localization result compared to the odometry. You can see the great difference between this odometry and the SLAM result. We actually did the excavation experiment using the robot. test bed is about 5 meters length, and we use the ALC block, which corresponds to 4 megapascal of the strength. In between the ALC blocks, there are some silica sands. So we drill the silica source first. Okay, and then the ALC block is drilled. So this excavation process is repeated until we reach the goal. Okay. And we are also developing some visual odometry. And currently we are developing the visual inertial odometry using the combination of the vision sensor and the iMU sensor. So we made this algorithm called ALVIO, Adaptive Line Point Feature-Based Visual Inertial Odometry. So we combine the point feature with the line feature and perform the visual odometry. So compared to the BINS mono, which is the state-of-the-art algorithm in the visual inertial odometry, we can decrease the error about 16%. So this is the third floor, and then we go down the stair to the second floor, and again, we form the roof for the second floor and go upstairs and go to the third floor. And this is for the indoor and outdoor situation. So we make the grate roof and make the roof closure in here. Okay, this is for the Euro C data set, which is the open data set for comparing the visual odometry result. So compared to the BINS original, we apply our method, then we can decrease the error by 16%. So the next topic is the structural monitoring for disaster prevention. We apply our SLAM techniques for aerial environment. For example, for the bridge inspection, we can use the UAVs. So we use the similar visual inertial odometry, and using the 3D LiDAR, we form the node generation, and then by forming the constraints and optimize the graph, and pose is estimated using this hierarchical graph SLAM. So we develop our own hierarchical graph SLAM architecture to optimize this robust trajectory. So we have two test environments in South Korea. So this is the under the bridge. So in the under the bridge, we cannot receive the GPS signal regularly. So in that situation, we can make the visualization odometry as well as by matching the 3D LiDAR scans, we can build a map as well as localizing itself. So the advantage of this method is that because we are getting the under bridge images like this, we can analyze this image, and if we find the crack, then also we can localize this crack. So exact location of this crack can be obtained using this SLAM technique. If you use the drones in the outside, like the bridges, then it is very vulnerable to the disturbance from the wind. So we have to make the drone robust to the wind. So we made this system called KAIST wall climbing drone. Okay, you can see that we also use the auxiliary arm, and this drone can climb the wall using this auxiliary arm. In spite of there some wind, we can obtain the stable images from the bridges. And also we have applied our KAIST to various environments. Okay, we have applied our KAIST to various environments. Okay, this is for the fire disaster situation. So this KAIST has been used for scouting this fire disaster situation and also climbing very narrow space. This drone can endure very hot thermal situation. We use the aramid fiber to protect this body. So by wall climbing capability, we can inspect the very narrow space. Okay, we can also apply our drone for climbing the glacier wall. And also we have developed a soft perching mechanism for reducing the impact on the perching. And this drone can climb the wall, and also if you install the cleaning device, then we can clean the glacier walls. So this drone can be applied to various areas like inspecting and cleaning, and also cleaning the solar panels and inspecting the aircrafts very quickly. We are developing the scout drone for fire disaster situation also. In the fire disaster situation, various sensors are useless actually. The cameras and LiDARs are useless, so we have to develop some kind of localization algorithm, localization device to cope with this kind of situation. So we try to localize the UAV using the UWB signals. So we have developed tightly coupled UWB IMU odometry called UIO. So in the tightly coupled system, we actually estimate the bias and the scaling factor of the gyroscope and accelerometer at the same time, as well as estimating the pose and velocity or the angle velocity of the system. So this is the overall flow chart of the UIO system. Initially, we guess the initial position and state vector is set, and then prediction, observation, and state and covariance update is iterated using the iterative EKF. And in the prediction and observation, we use the UWB and IMU information. So we installed 4 tags on the UAV, and 1 UWB anchor is deployed in arbitrary location, and we can actually estimate this location of the anchor. So we don't have to specify the initial location of the UWB. And we use the 3-axis IMU, including the gyroscope and accelerometer, as you can see. And then we can compare our proposed method with the conventional method proposed by this paper. So you can see that we use the ground truth from motion capture from OptiTrack, and state-of-the-art algorithm here provides about 60 centimeters of RMSE, while our algorithm about 20 centimeters in RMSE. We can compare our result. Okay, this is the overall integrated navigation architecture. The 4 labs are involved in this project. So we use the IMU and UWB for localization, and by forming the graphs from other sensor data, we can optimize the graph and generate the current pose. Okay. So this is the experimental setup in the pilot test area. So this is the SLAM estimated trajectory, the red one, and the blue one indicates the test planning result. So this UAV will follow this trajectory. So autonomous navigation is performed like this way, and you can see that we have successfully circled this area. In the mild smoke situation, we are also performing the experiments. So we are manually moving this drone, and using the combination of the UWB and 2D LiDAR, we can estimate the vehicle pose like this way. Because we are using the LiDAR again, we can also get the map of the environment like this way. Okay, this is the result. Thank you for your attention, and are there any questions?